This video is intended to give you a review of the upcoming exam number 2 here in numerical methods. So let me just start by giving you some of the basics of exam number 2. We'll have 4 problems on the exam. And since it's a 50-minute exam, each problem will have to be fairly short, so I won't have an expectation of a long worked out problem, but obviously, each one will have its own work with it. It will cover blocks 3 and 4 exclusively. Okay, so that includes the homework that you had due before spring break, and also the homework that you have due before the test, right before the test. Blocks 3 and 4 cover quite a bit of material. So I've got quite a bit to choose from, so I'm going to go over that here. But before I begin that, I also want to emphasize that there'll be no programming in this, and also there'll be nothing in this that obviously would require a computer, because you will not have a computer at the testing here in the room. So you won't be able to do things like spline fits, and you had homework that required Excel for certain parts that we did, and I'll kind of mention that toward the end. But right now, all I can do is do stuff that you can do in class. And so there's homework that you had an optimization, for example, that you had multivariable optimization that you did in Excel using the solver. I can't do that in a test. Okay. Also, you did homework where you did a program either in Excel or MATLAB that you did multivariable optimization with nonlinear using your own program and a method that I talked about in the videos. Again, I can't do that in class. So I'm going to just focus on today is what can we do, what are some of the subjects we can do, and how you can best prepare for the exam. Okay, so let me go over, I've got 7 things I think that are definitely fair game that could be covered, and some of them are a little bit related. So topic number 1, called Gauss, okay, or Gauss elimination. Okay, and recall what that's really doing is we're solving AX equals B, where A is some matrix of some size, it's a square matrix, right? Times X, which will have, X1, X2, let's just say, for example, it's X3, okay? Now, I could do, I doubt I'll do a 2 by 2 because that would be too easy. A 3 by 3 usually hits the sweet spot as far as size of the matrix goes. A 4 by 4 might be a little bit big, but, it might be fair game. Let's just pretend it's a 3 by 3, but it doesn't have to be a 3 by 3. So we've got this and this form. So you'd have matrix A, and I would give you those as numbers, right? And vector B, I would give you those as numbers. And you would be solving for X1, X2, and X3. Also, I don't have to give it in matrix form. I mean, that's certainly one way to do it. I could just simply give it to you in equation form. I could say something, one of the equations might be 3x1 minus 5x2 plus x3 equals 7 or something like that, right? And I could give you 3 of those, 3 equations, 3 unknown. Or I could do 4 equations, 4 unknown, or whatever, right? And then I would expect you to be able to put those equations into matrix form. So I may give you the matrix form, I may just give you the equations, you can put them into matrix form. It doesn't have to be x1, x2, x3 as the variables. It could be x, y, z. Right? It doesn't really matter. Okay? But the whole point is to use Gauss elimination to solve for x here. And so you should know how to do that. You should have done that for your homework. Now, one thing I will say in a problem like this is certainly you can use your calculator, and you can use all sorts of techniques on your calculator to get the answer. But if I ask you to do it via Gauss elimination, you're going to need to show me that in Gauss elimination, okay? So just having the right answer, that's great and all, but that's not really full credit. That's not a lot of credit because I'm asking you to show me using this technique, okay? So just make sure you know how to do that. But of course, always encourage you to make sure you know what the right answer is so that you can check your Gauss elimination and make sure you're good. So that's certainly one thing. You should know how to do that, not too hard. The next thing is a very related topic, but I kind of decided to make it its own, and that is inverses, the matrix inverse, using what we call Gauss-Jordan elimination. Okay? Now, Gauss-Jordan is just like Gauss. I mean, we're trying to solve the same problem here. Okay? But the advantage of Gauss-Jordan is that you can actually use a numerical technique to calculate the inverse of a matrix. And recall what you do. If you want the inverse of matrix A, you set up a larger matrix that you augment it with the identity matrix. And then what you do is you try to use Gauss elimination techniques to then transform that matrix such that the left side becomes the identity matrix, then the right side will become A inverse. Okay? And so it is a way to get the inverse of a matrix by hand. Pretty nice way of doing that. Again, you could certainly do that by your calculator. So if I ask you to do this, show me Gauss-Jordan to get a matrix by hand, you could use your calculator to then, give me the right answer. Make sure you know that the answers confirm your answer. But if I ask you to do it, you got to show me it, right? And again, the whole point of this is to build linear algebra concepts, okay? Because some students ask me, well, why should we mess with this? I know how to do this on my calculator. Yeah, I know. But the point is that we're building some concepts of linear algebra by going through some of these practices, okay? Also, I may ask you to actually use that matrix inverse to solve an equation, a system of equations, or what have you, okay? So make sure you then know how to use the matrix inverse to then solve a system of equations, okay? Because obviously x is equal to A inverse B, okay? Right? So you need to know how to do that as well. So those are some things. I may give you something in that realm just so that you have some experience that can show me that you do that. Okay, number 3, optimization. Optimization. There we go. That's better. Okay. When we talk about optimization, I'm only talking about single variable. Okay? So talking about single variable, and I'm really talking about 2 techniques, what I call Newton's method and I'm talking about golden section. Okay? So I've got those 2 methods. The Newton's method, as you recall, it looks just like Newton-Raphson. We're trying to optimize a function of a single variable. It looks like this. xi plus 1 is equal to xi minus the function, the derivative evaluated at xi, divided by the second derivative evaluated at xi. Now, I typically, and I probably will not give you this equation on your equation sheet, but you will have the Newton-Raphson equation, which is the same thing, except instead of it being the derivative divided by the second derivative, it's simply the function divided by the first derivative, okay? And so you need to know that with Newton's method, we're not trying to solve a roots problem, okay? With Newton's method, I'm not trying to do this, okay? That's not what Newton's method's for, okay? What Newton's method is for optimization. Okay, we're trying not to find the x that causes the function to go to 0, but instead the x that maximizes or minimizes. Okay. Now with Newton's method, I'm going to have to give you an initial guess. I'll have to tell you what the initial guess is. Okay. Now when you get the result, you really don't know if it's a max or min. So you would have to substitute that into the original function to determine whether that was a max or min. Okay. So I may have you do something like that to do that. Okay. Then there's, of course, the golden section, and that has its own equations that, of course, I will give you on your equation sheet, and I'll show you the equation sheet at the end here. So that's certainly another topic that you need to make sure you review and know how to do it. It can be a little confusing for students. I spent some time in class. Of course, there's videos. Make sure you review it. You know how to do the technique. And make sure you read the problem carefully to know that we're trying to either maximize or minimize the function, because whether you max or min has a bearing on how you do the golden section. Okay, and so that is certainly another very important topic. Okay, number 4, obviously statistics. Okay, and you're going to get all of these things. These are definitely review the homework example that you have. Okay, and recognize that if I ask you for confidence intervals, that a t-table will be provided along with the formulas. Okay, I'll show you the formulas. So make sure that you know the basic statistics that we're going to test: mean, median, mode, and mid-range. Okay. Standard deviation, sample standard deviation, that equation is provided for you. And then I'm also giving you the equations for the upper and lower bounds of confidence. Okay, and I'll show you those as I show you the equation sheet. Make sure you know how to use those, and recognize that you will get a t-table. So if you open up the test and you see a t-table, you'll know, oh, I have a stats problem. Okay, I'm going to have a set of variables, set of numbers comes from somewhere, and I'm going to probably have to calculate all sorts of things, basic statistics about those numbers. Okay, so that's something that that you'll have to consider. Okay, so that is number 4. Number 5 is curve fitting. Okay. Okay. In particular, what we're going to do when we do curve fitting is the pseudo-inverse. Okay, so make sure you know how to do that. You all have homework example on that. And recognize that I could ask you to fit a polynomial or a line or both. Okay, so in this case, I'm going to give you XY data, or it doesn't have to be XY. It could be QT data or whatever. It doesn't matter, right? But essentially XY data and paired data, and you're going to have to fit that data to either a line, a polynomial, or whatever. So that is certainly something to that you should have practice with on your homework, and there's an equation that I'm going to show you in the equation sheet that I gave you as well, okay, for curve fitting. All right, number 6, numerical integration, of course. Okay, and then in this one you got 3 techniques: trapezoidal, you've got Simpson's 1/3, and then also Simpson's 3/8. Okay, so you've got 3 techniques. Again, I give you those equations in the equation sheet, and you should be able to apply them for a single numerical integration. Okay, and then finally, last of the 7 is related to number 6, and that is looking at double integrals. Okay, I could give you a double integral that I ask you to do using techniques trapezoidal, Simpson's 1/3, Simpson's 3/8 as well. Okay, now in the example numerical integration, I may have you do it several ways. Okay, and compare. And obviously with numerical integration, your calculators probably have tools to do that analytically or numerically or both. You should be able to check your work. It's basically what I'm saying. Okay. Now, in all this, you will have to move fairly quickly. You have 4 problems. I've got 7 areas here with your 4 problems. I will tell you this, guaranteed, okay, that you're going to get something from area 3, optimization, and area 6, numerical integration. Those are guaranteed to be at least 2 out of the 4 problems. It's possible I could even give 2 problems from section 3, maybe 1 Newton's method, 1 golden section, but I'm leaning against that. Most likely one problem from 3 and one problem from 6. And then I can pick 2 problems from the other 5. And again, you've got homework on all these things: Gauss elimination, Gauss-Jordan. You've done things like that. Stats, you definitely had a homework problem on that. Curve fitting and the double integral. So let me show you the equation sheet here. When you first see this, you'll notice some familiar equations. You'll see how some of the equations that we've been dealing with since the beginning, Taylor series, and you'll notice there that I gave you the Newton-Raphson equation. That's not the Newton's method equation, okay? So you'll have to modify that. I also gave you the secant formula and some other stuff there for nonlinear systems of equations. But okay, now we got some ones you're going to need. Pseudo-inverse. Okay, I gave you pseudo-inverse. You can see that. Okay, I didn't give you everything, but at least I gave you the basic form of pseudo-inverse. Okay, your calculators might be able to do pseudo-inverse automatically. I'm not sure about that, but you probably, or you certainly could program your calculator to do it. I also gave you the formulas needed for golden section, for the stuff that you'll need for that. And I gave you the formulas needed for the trapezoidal method, Simpson's 1/3, and Simpson's 3/8 method. And finally, I gave you the formulas here for standard deviation of a sample and the upper and lower bounds, confidence bounds. Okay? So I think I've given you everything you need as far as formulas for this upcoming exam. But if you feel like I'm missing something in this list, feel free to email me, and I'll certainly consider adding it. But a lot of these things are really just techniques that you know how to do. I can't get it to be too difficult because you really have less than 15 minutes per problem. So I have to make these fairly simple. I would say in general this is the best test for students. So I'm hoping to have a lot of good scores with this. Just make sure you know how to do the things that I've reviewed, and you should be fine.